let me start introducing Herman. So Herman has an undergraduate degree at University of Buenos Aires. He grew up in La Pampa, in Argentina. And after graduation, he worked in a variety of roles in industry in Argentina. And so he's thoroughly familiar with cropping systems. He got the opportunity to work in David Bullock's lab. So he has a master's degree in economics at University of Illinois. And then in the year 2018, he started to do his research towards his PhD in crop science. And that's why we are here today, to see the result of that work, okay? And with that, Herman, you are in charge of the presentation.
Okay, let's see. Can you see the screen?
Yes.
Okay. Okay, so thank you, Nico, for that introduction. Let's start with the presentation. The title is the evaluation of nitrogen management strategies and policies with high throughput crop simulations. There we go. As an introduction, I would like to explain the reason or the problem that we will try to solve in the different chapters of the thesis. It is called the nitrogen challenge, and it consists on maintaining high production and profitability while reducing the environmental cost of agriculture. Basically, we have these three variables here that they are related, and there are trade-offs between them. So we have to choose the right nitrogen rate that is high enough to guarantee adequate farm profits. But if it is too high, it has environmental consequences, especially in water quality. To give an idea about the dimension of the water quality problem, here we see a map of the US. In green is the area where most of the crops are planted, and in red are the cities. For one of the main crops is corn, and in corn we need to add nitrogen because it's one of the most important nutrients. When we add more than what the roots uptake, the nitrogen stays in the soil and there is very mobile. So when it rains, the water will carry the nitrogen out of the soil, and it will go to different water bodies, and in all of them it can generate different environmental impacts. So for example, if it reaches groundwater, then that water it can have health issues for humans drinking it. Or if it goes to lakes or river, it produces what is known as an algae boom. So algae grow a lot, and when they die, bacteria decompose them, and they take the oxygen of the water. So then no fishes can live in that water, and the water becomes very green, and it loses the recreational value. So all this area, the nitrogen keeps moving, or most of the nitrogen goes to the Mississippi River. So there, the nitrogen concentration is high, and it moves down to the Gulf of Mexico, creating there what is probably the most observable impact of nitrogen pollution, which is the dead zone of the Gulf of Mexico. What makes this more difficult is that we need to, the nitrogen rate is not constant. It depends on the weather, especially during the critical period of the crop. But we need to apply the nitrogen early in the season when the crop is short, so we can go with machines and apply it. So we need to make the decision without knowing the weather and the soil conditions that will happen around flowering. And that makes that there is a lot of uncertainty when providing recommendations. The outline of this presentation follows the same outline of the thesis. On chapter 1, I will explain how we generated and calibrated the data using crop modeling. In chapter 2, we will compare different nitrogen management strategies that can be used to provide recommendations. On chapter 3, we will focus on 2 of them and look at them into more detail. And in chapter 4, we will see the use of policies to induce farmers to use less nitrogen. So basically, chapter 1, we created the data that was used in the following chapters. Chapter 2 and 3, we will see different ways of recommend nitrogen better under current market conditions. And chapter 4, we will say, okay, this is the best we can do with current market conditions. If we want to reduce leaching more, we need government interventions. And we will compare 4 policies that can be used for that. So chapter 1 is crop model calibration and validation. For the simulations, we use the state of Illinois as a base. There we made a grid that is each square or each cell is 10 by 10 kilometers. On each cell, we place 4 fields. And for each of the fields, we selected the 3 main soils. We use AppSim for the simulations. That is a crop modeling software. And we obtained the information that described the soil from Sorgo and the weather from DayMed. We simulated a corn-soil rotation. For that, when 2 fields had corn, the other 2 had soybean, and then they alternated the following year. And we did that over 30 weather years. So each field had corn 15 times, one every other year, right? Each time a field had corn, we simulated increasing nitrogen rates from 0 to 320 with 10 kilograms hectare per increment. So that is a total of 33 nitrogen rates. When we consider that we had 4,270 fields, so all those points there, the 3 soils, the 15 times that it had corn, the 33 nitrogen rates, that was a total of more than 6 million simulations. So it is a pretty big database. We calibrated the simulations using data from real experiments that were run by the Maximum Return to Nitrogen project. That is a project from the extension service of the university, and they have 461 trials here in Illinois. We compare the main variables that will affect our results, including the yield shape, the EONR distribution. I want to explain what is EONR because I will use it a lot in the presentation. It is the economical optimal nitrogen rate. So when we have a profits curve of the response of, the response of the crop to nitrogen, there is a nitrogen rate that maximizes profits, and that is the EONR. Then we also compare the yield distribution. And finally, this is not from MRTN, but we compare the nitrogen leaching simulated from the fields with the real concentration of nitrogen in the Mississippi River to see if there is some correlation between them. And we found that they are related. When there is a peak of nitrogen on the simulations of nitrogen coming from the fields, 1 month later, there is a peak of nitrogen in the Mississippi, and the same happens with the bottom part. So we can think that the nitrogen is slowly moving from the fields to the river. In the main variables, we see similar distributions. The crop model capture the pattern that is observed in the state when we move from south to north. Basically, what happens is that when we move north, the soils have higher organic matter. So the yield with 0 nitrogen is higher because the soil is providing more nitrogen. And also the EONR becomes lower. And the yield increases in that direction because the growing conditions are better and the soil are better. Not necessarily the organic matter, but there are many factors that make that happen. So the takeaways of that first chapter is that we use an innovative calibration and validation process. It's innovative because many research compare simulations in a site-specific way. So they compare how AppSim performed with some real data in that same place. Here we compare the distribution of both populations to see if our population of yield curves is or represents the population of yield curves that are in the state. We saw that AppSim captured the yield, the response to nitrogen and leaching patterns in the state, and that crop modeling can be used to generate the data set that we need in the following chapters. The chapter 2 is modeling the economic and environmental effects of corn nitrogen management strategies. The objectives are to compare different strategies. Someone is unmute, I think. There. Okay, so the objectives are to compare different strategies that can be used for nitrogen recommendations in the long term and over multiple fields. So what happens is that in nitrogen management, there are different companies and different researchers working on this, and there are different options that they propose to solve to provide recommendations. Some people say that variable rate is the solution and that we need to find the management zones on the fields, and that will increase the accuracy of the recommendations. Some other groups say that we need sensor and we need many predictor variables, and that will allow us to provide better recommendations. Some people say that we need more trials. So here we want to compare these different approaches all together using the same data and over a long period of time. The methodology, we started with the crop simulations that I explained in the previous chapter. We had a trial period that those were the first 10 years of the simulations, and an evaluation period that were the following 20 years of the simulations. During the trial period, we collected information of nitrogen responses, crop responses to nitrogen. So the 33 rates that I mentioned, we use that to optimize 10 recommendation strategies that I will explain later. And then we use those recommendations over the evaluation period. So on a different period of time to provide recommendations and to compare them and see how they perform. The treatments, or those 10 strategies, are a combination of 4 factors with 2 levels each. One of the factors is the origin, and this is about where the data of the trials is coming from. It can be regional or local. For the regional case, that means that we obtain we made the trials in those triangles that we see there. Those are 240 research stations. So they provided data that was used to optimize the models, and then the models were used in the other fields that are blue dots there. In the local approach, instead of having research stations, we did the trials on the same fields where then the models provided the recommendations. So we say on each of the fields, we did 10 years of trials, we optimize the model, and then we use them in the following 20. The model is about how we analyze the data, and it can be static or dynamic. They all start with trial data. Here we see an example of some yield curves. The static method is the one that is used by the MRTN group that I explained earlier, that currently provides recommendations. And basically what they do is they transform the yield curves into profit score by multiplying by the price of corn and subtracting the cost of nitrogen. Then they aggregate all the profit score from a same region. So for each of the 3 regions that we saw here, and they obtain the nitrogen rate that maximize profits on each of the profit score. So at the end, we will have something like this. It is one recommendation for each of the regions. And we say that it is static because after this, it doesn't change over time. If we have a dry spring or a warm spring or any conditions, the model will tell us to apply this rate that was obtained. It doesn't adjust for those conditions. On the other hand, the dynamic option starts with the same trial data, and for each trial data, for each trial, we will obtain the EONR. And the main difference is that they use predictor variables. Here I put some examples to explain the variations in the EONR. In our case, we did the dynamic model with a random forest model. We tested many options, and this one was the best. And so then we use these variables to obtain the EONR, and it is dynamic because it changes over time. If there is a warm spring or any conditions, the model will adjust the rates considering those new conditions. The information is about the predictor variables. So it didn't affect the static because it doesn't use predictors, but in the dynamic, there are many variables that can be used to provide recommendations, and they have different costs. Some of them are more expensive than others. So we made two sets of variables. One is the low cost, and those are variables that can be obtained by sensors, so they don't require much effort or an extra cost, and including leaf area index at V5, weather conditions, and that can be obtained by a weather station. The high information includes all the low cost plus soil sampling. And for soil sampling, we measure organic matter at V5, soil water at V5, and nitrogen in the soil at V5. The technology is about how we apply those nitrogen rates. So in the case of uniform rate, that means that we provided one recommendation for the whole field. And in the case of variable rate, we provided one recommendation for each of the 3 soils that a field has. So when we combine all those factors, we get this table here with 10 nitrogen management strategies. Only one factor is changing every time we move in this table. The first one is the baseline, and that is what it represents the current approach to nitrogen by the extension service of the university. So this is the MRTN recommendation. It is regional, it is static, and it is uniform, and it doesn't use any information. The second one is like the first one, but instead of static, it's dynamic with low information. The third one is like the second one, but instead of uniform, it's variable rate. The fourth one is like the second one, but instead of low information, is high. So that means we are adding soil sampling. And the fifth one is like the fourth one, but instead of uniform rate, is variable rate. All these are regional and all these are local. And in the local, we follow that same sequence that I just explained. We did this on purpose, and the idea is that then when we get the profits with one method and we subtract another one, we can get the value of that factor that is changing. So for example, when we subtract the profits of 3 with the profits of 2, that is the value of variable rate under low information. When we subtract the profits of 4 with 2, that is the value of doing soil sampling. So let's go to the results. This table has a lot of information. It is coming from 4,030 fields over 20 years, and all those results were aggregated in one table. The main columns are nitrogen leaching and profits. Those are the ones we are mostly interested in. The takeaways first are that regional didn't perform, regional are better than local. So basically local didn't perform better than regional. And since local requires more effort and a higher cost because we had to run on-farm trials on each field, if they don't increase profits, it is better to have fewer research stations, and that will provide enough profits or the same profits. The dynamic tools reduce nitrogen leaching. If we compare in the regional case, the dynamic tools did not increase profits over the baseline, unfortunately, but they reduce leaching. So that is their main advantage. Then variable rate did not provide value, at least in the state of Illinois with our flat soils. Variable rate, when we compare the pair of strategies that only differ in variable rate, they did not increase profits, only in this case by $2, but that is not enough to compensate for the extra cost that variable rate will have. Finally, if dynamic tools are going to be used, they need high information. What we mean by that is that if we use dynamic tools without soil sampling, we actually have lower profits than the most simple static option. So if we are going to try to be more accurate, we need to have good information. And in all the cases, that included soil sampling and organic matter and nitrogen in the soil were always the variables with the highest predictor power in the models. Finally, I want to use this table to introduce the following chapter, because something that we saw here puzzled us, so we want to explain it better. When we compare, the baseline is the static method, is very simple, just 3 nitrogen rates, 1 per region. The fourth one is much more complex. It uses machine learning. It uses many predictor variables to try to recommend nitrogen better. When we look at the RMSE, we see that the more complex is better and it is more accurate in the recommendations, but it did not increase profits over the static method. We also saw this in literature and some papers that compare tools. The MRTN was always the most profitable or among the most profitable. And we want to understand why. How is it possible that a more accurate tool did not increase profits over a much simpler tool? So that's why we made chapter 3, that is the comparison of dynamic versus static nitrogen recommendation tools. The objectives are to explain why tools, dynamic tools, even being more accurate, do not increase profits over simpler static methodologies. For the methodology, we started with the simulations that I explained in chapter 1. We had the trial fields. Those are the 240 research stations that we use to obtain nitrogen response information. We use that to optimize 2 models, the static and the dynamic. It's the first and the fourth of the previous chapter. And we use those models to provide recommendations on the evaluation fields. In this case, we use the leave 1 year out approach. So instead of the 10 years and the 20 years that we had before, we here we are training with 29 years and leaving 1 year out, and then providing recommendation for that year that was left out, and looping over all the years to obtain recommendations for each of them. For the results, first, I want to show how variable the EONR in the state is. So here we see on the x-axis the years, and the graph are the box plots of the EONR, and each point here is a field. So a field on a given year. We see that some years the median was above 200, some years it was very close to 100. Also, the variation between the fields, some fields is very small, so most of the fields had a similar EONR, and some others the variation is much higher. The dynamic tool, the static tool deals with this variation in a very simple way. It provides one rate that works more or less well in all the cases, but it's constant. The dynamic tool is trying to recommend 1 nitrogen rate for each field and year. And it does that. It is more accurate, but it does not increase profits. So to explain why, when we have these 2 figures down here, on the left, the x-axis is the nitrogen residual. So that is the difference between the nitrogen rate recommended by a tool and the final EONR. The blue line shows the profits curve and is represented as the profits change to the maximum. So what happens when a tool recommends the best rate, so it hits the target, the profits are at maximum. When the tool over predicts, there is a loss on profits because we are applying nitrogen that did not increase yield, so we are wasting nitrogen. When the tools sub-predict, we are losing, there is also a profit loss, but in this case it's because of a yield penalty, since the crop was limited and didn't have enough nitrogen. The key thing to see here is that the loss to the right is lower than the loss to the left. So the cost of over-predicting is smaller than the cost of sub-predicting. Leaching doesn't follow that pattern, and it always increases when we add more nitrogen, and after the EONR, it increases linearly because the crop is almost at full capacity and all the nitrogen we add will eventually leach. When we look at where the 2 tools that I mentioned recommend, we see that the static tool is biased to the right. So 60% of the time, the MRTN tool is over-predicting, and a more accurate tool, by definition, will try to be closer to 0, but they are not perfect. So 50% of the time will be under-predicting and 50% of the time will be sub-predicting. When we move that to this graph, we can think that the dynamic tool will provide recommendations more or less in this area, 50% of the time above and 50 below. And the static tool, this is a bit exaggerated, but will be more biased to the right. So this explains why a tool that is more accurate provides the same profits than the static tool. The dynamic tool, 50% of the time, is paying that higher penalty than the static tool is avoiding by over predicting more times. So the takeaways are that complex dynamic tools face disadvantageous economic conditions. What we mean by this is that since they are more accurate, 50% of the time, they will pay that higher penalty than tools that are more on the bias to their over prediction. They don't pay that penalty. We say that it is unlikely that they will be accurate enough to overcome those disadvantages. By this, what we mean is that in our simulated world, there is no random noise. What the Chrome model is telling us that a variable is, that's what it is. There is no lab error or instrument measurement error or anything like that. We have many trials and many years of data that were used to train the random forest. If we were not able to achieve an accuracy high enough to increase profits over the static tool, we think that it will be very difficult to do that with real data. When we compare the RMSE that we obtain with this data is much lower than the RMSE that we see on papers that compare tools with real data. So we think that our tools were very accurate or more accurate than what we can obtain with real data. And yeah, if they did not increase profits, will be difficult to do it. Both tools can reduce nitrogen leaching by 5%. By this, I show that the dynamic tool lowers nitrogen leaching because it is more accurate, but I didn't show that. But if the static tool, instead of recommending the nitrogen rate that maximizes profits at the peak, recommended a nitrogen rate that is that makes profits $1 below that peak, that will reduce leaching by 5% without hurting profits much. And finally, the implications are that we need to rethink the goals of nitrogen tools. What we mean by this is that if we keep thinking that we will be accurate enough and that will increase profits for farmers, that will probably not happen. So these tools do not increase profits, so farmers will not adopt it. So we need to have that in mind and act in consequence or find other ways of making these tools attractive for farmers that are not profits, or I don't know, find policies or something that increase adoption. Chapter 4, trade-offs between profits, yield, and the environmental footprint of different nitrogen regulations. The objectives of this work were to compare 4 policies that can be used to reduce nitrogen leaching even further. The policies were, the first one is the price ratio modification. The price ratio is the price of nitrogen divided the price of corn. Currently, that ratio is 5, and we increase it by increasing the price of nitrogen from 5 to 20 by, this will be a tax on nitrogen. The leaching fee, the idea is that if we can measure the leaching coming out of each of the fields in the state and charge farmers a fee for that leaching. So we tested different levels of fee. Currently, that is impossible, but we think that with digital agriculture and crop modeling, maybe in the future we can find ways of measuring leaching from the fields. The nitrogen balance fee, it was calculated with this equation, that is the subtraction of the nitrogen added as fertilizer and the nitrogen removed in the grains. The idea is that if we are adding more nitrogen than what we are harvesting, that nitrogen will stay in the soil and eventually will leach. So we charge a fee on that simple indicator that is the nitrogen balance. Finally, the last policy was the voluntary reduction of nitrogen rates. This is simpler. Instead of using those economic instruments to lower the nitrogen, we will ask farmers to reduce nitrogen by a certain percentage in exchange of a compensation that will cover the loss in profits. To remain realistic, the range of values explored by these sub-levels that I show in each of the policies was limited to those that did not reduce yield by more than 5%. the idea of this is that if we reduce, if we make a tax so high that reduce yield by more than 5%, that will change the rotation that farmers do, or there will be so few corn in the market that the price will go up, offsetting the policy. So we try to limit that and to, without decreasing yield by more than 5% and assuming that that will keep the other things equal. The methodology, we started with the same simulations from chapter 1. We have the trial fields. Those are the 240 research stations that provided nitrogen response information that we use to optimize, in this case, only the dynamic tool, so only the random forest model. This is where the policy implementation comes into play. When there is a tax, let's explain the tax. So for example, we have the trial information. If nitrogen is more expensive, that will make that the EONR will be lower in each of the trials. So we are considering the policy when we in the training set. And similarly, if there is a fee on leaching, that will also lower the EONR. And then we are applying those models on the evaluation fields. Again, we are doing the leave 1 year out approach. So training with 29 years and leaving 1 year out that was used for evaluating. The results here, we see the trajectory of the main indicators. Each column is a policy. Each is one of the 4 policies. Each row is a variable, is one of the main variables that I will explain. And in the x-axis, we are increasing the sublevel of the policy. So the policy is becoming more aggressive. In this case, the tax is being higher or the fee is being higher in these cases, or we are asking farmers to reduce nitrogen more. In all the cases, the more aggressive policy makes that the nitrogen rates used by farmers decrease. That makes that the nitrogen leaching is lower. The farm profits also decrease. The government collections is the money that the government is obtaining from the tax or from the fees. They increase, and we assume that the government collections were returned to farmers by region. So all the money that was collected from the fields in a region was bundled together and then paid back to farmers as equal payment per hectare on the fields on that region. After the government collections are returned, there is still a loss of income by farmers because they are not using the original nitrogen rate that maximizes profits. That is what we call the policy cost. And we also assume that the government or us as a society will compensate for that, that loss of income. So this is what really matters. We want to see the cost efficiency of the 4 policies. Here we have on the left the policy cost. So that is the cost that we will have or the government will have to achieve certain reduction. And on the x-axis, we see the nitrogen leaching reduction. Each of these is a region, but let's look at the last one that is for the whole state. We see that small reductions can be obtained at low cost, and it increases, the cost increases exponentially. Looking at the values, we think that a reasonable target would be a 20% reduction, because that will be a cost between $30 and $37. And we will, when we scale that up, considering the area of corn in the state, that is more or less $130 to $160 million. And when we compare that with other expenses that the other environmental programs have in the state, that is more or less the same amount, and is much lower than what is currently spent on subsidies. So it seems like a reasonable alternative to include this type of policies. When we compare the 4 policies, the green line is the leaching fee, and it was always the one with the lowest cost. The difference is not high, but it is more or less $7 in the case of the 20%. The reason that the leaching fee is more efficient is that it is directly charging the problem. It is, so the nitrogen leaching is an externality. When you put a fee on that, you are internalizing the externality, and that makes the optimization more efficient. So the random forest in this case learn how to reduce nitrogen rates more in conditions that will lead to higher leaching. The other policies do that indirectly, and that makes them that they are not as efficient as the leaching fee. The takeaways is that policies allow to reduce leaching by 20%. The nitrogen leaching fee show some benefits, the lower cost that I just explained. It also had a better smoothing effect. That is, we want to reduce leaching more in fields that have high leaching to avoid the formation of hotspots, and the leaching fee did that better. And it also had a better internalization effect. The idea is that we want to reduce profits more in fields that have high leaching, and that will create synergies in the system, and farmers will adopt other tools that will help them to reduce leaching in those fields with high leaching. So for example, if the policy is making their profits lower, they will start to use practices like cover crops or bioreactors to reduce their leaching even more. And finally, the policies are reasonable alternative to be incorporated into the current nitrogen loss reduction strategy. This is a document that recommends policies to reduce nitrogen leaching in the state, and our policies will be the second one in terms of the capacity to reduce leaching, and the fourth one in terms of cost. So finally, as a general conclusion of the thesis, if you remember, we say that we want to solve the nitrogen challenge. So what did we learn about it in the different chapters? On chapter 2, we learned that variable rate is not the solution, and that regional models work well and might be better than local. On chapter 3, we learned that dynamic tools that improve accuracy are unlikely to increase profits. So this means that there is no incentive for farmers to adopt those tools. So we need to find other ways of creating incentives. Both static and dynamic tools can be adapted to reduce nitrogen leaching by 5%. Chapter 4, policies can reduce leaching by another 20%. And a fee on the pollutant has some advantages over the other policies. And finally, what we think is the main contribution is the general methodology. This idea of using crop modeling to generate a very broad data set where we know everything, and we can compare methodologies, training and testing with the same data over many years. We think that there is a lot more that can be done, and it allows to answer many questions that we haven't been able to answer with real trials, because it will require many trials, and that is expensive. So finally, I would like to say thank you to the 4 professors of my community, because they helped me, and every time I got stuck or I needed help, they were always there. The co-authors of the different chapters, the different papers, my colleagues, Agustin and Rodrigo, that we are always talking and helping each other. The IT support that helped me to run all these simulations in the cluster. The Climate Corporation, because I did 2 internships and I learned many of the skills that then I apply in this research. My family, my girlfriend, my friends, and everyone that was with me during all this time. And with that, I want to say thank you for listening, and we will take any question. You are mute, or...
Thank you so much, Germán, for this great presentation. I would like to know if there are any questions from the general public.
Hey, Nicolás.
Oh, Nahuel, you're mute, I think.
Nope, I think
Can you hear me?
Oh, okay.
Maybe I can hear you.
Okay.
Okay, thank you. First, Germán, thank you for to share this job, and obviously congrats for your result and your research, and obviously congrats for your committee. I have two questions.
Yes.
First, you mentioned, but I think that I don't capture very well the result, and so I think that you can help me to better understand. First, why or what is the main reason about that the variable rate technology don't generate more value than the typical farmer management or the uniform management? This is the first question. And another question, you work with machine learning, no? With the random forest with different dynamic variables. So what is the main dynamic variable that management the, the nitrogen, no? In general, about the optimal nitrogen rate or the nitrogen leaching? If you can share with more or information or explain with more detail, I think that you can help me. Thank you.
Yes. Okay, thank you. Thank you for those questions, are really good. So the first one about the variable rate, we think first that predicting nitrogen is very difficult. So there is a lot of noise. Yeah, and if we want to, we first need to learn how to predict nitrogen well for a whole field before maybe going into each soil. In the case of Illinois, it's a very flat area. Probably there is not much variation inside the fields. So that is affecting the results. In that paper, we put a map that shows the value of variable rate. And in some areas of the state that it is less flat, the value was a bit higher. So that could be one of the answers to the question. And the other one was about the variables, that which one had the highest predictor power, I think, right?
Yeah.
So in that case, one of the approaches to nitrogen recommendation is to use sensors and try to avoid Wilson sampling, because that requires effort and is expensive, right? At least in our results, we saw that organic matter and nitrogen at B5 were always the most important. And we also saw that if we don't include them, the profits are lower than a basic static tool. So apparently, or at least in these conditions, we need to do soil sampling, even if it is more expensive. If not, the profits are lower and we are just better by using some constant nitrogen rate. Is that an answer? Okay.
Yeah. Thank
Good. Thank you.
Is there any other question from the public?
Yeah, I have one if I have time.
Yes.
Okay.
Well, first of all, Herman, congrats. Great presentation.
Thank
I
you.
just have a quick question about your fourth chapter when you were talking and discussing about all the four policies. For you, I know this is kind of a more like a philosophical evaluation, right? But for you, looking at the four policies that you were talking about, which one do you think it would be more realistic or more easily implemented in the state? It feels like I don't know if this is some sort of, this is what regulation looks like when we're trying to tax fertilizer or making farmers to pay a fee or something like that. I was just curious to see what do you think about that, or if you have thought about that.
Yeah, really good question. It's on the paper we try to present them all and to show the benefits and cons of each of them, and it's difficult to choose one, right? I think in terms of implementation, probably the tax will be the easiest one to implement because it's easy to control. You just put a tax on nitrogen. But what we saw there is that you need to put a tax that is very high. You need to increase the price of nitrogen to more than double of what it is now. And that will probably make many people unhappy. So it might be easier to implement, but it will have a very high political cost. In terms of efficiency, the nitrogen leaching fee was the best one in many things that we look at. When you charge directly the pollutant, that has a lot of benefits because farmer will not only reduce their nitrogen rate, it will also adopt cover crops, it will do whatever thing they can do to reduce that leaching. And they will choose what is the best practice on each of the conditions. So that will make that economically it works very well. They will choose the cheapest practice that works well in their conditions, and it's not us who are telling them what practice they have to choose. They will find what works better in their fields. So I think that will be the best. It's very difficult to know because in nitrogen you can't measure how much nitrogen is coming out of the fields. But things are changing. We have crop models. We have, I don't know, maybe someone comes up with a sensor or something you can place on the fields and it estimates leaching, or I don't know, technology can provide a solution for that maybe in the future. And for example, in carbon markets, we are using crop modeling to estimate how much carbon soils are capturing or things like that. So maybe we can make this policy more voluntary and say that farmers will get paid for reducing the nitrogen leaching if they accept this methodology that we are using to measure it. So I don't know, we provided the values and we show that it works better and by how much. And that maybe provides incentive for further research in ways of making it possible. So yeah, thank you for the question.
Okay. Thank you. We have time for one more question. If anybody's on the fence. Otherwise, if it is, you can also send us an email with questions. We can reply them to either to Germán or me or both. Okay. So thank you all for your participation. Here, what we're going to do now is we're going to switch to another phase of the defense. So this part won't be public anymore. So first of all, I am very grateful that everyone came and support Germán in different ways through this point. I know you're very special for him and for us. So yeah, anyway, we will be available for questions later directly or by email or so on. Okay.